My name is Alexander Bolyakov, and today I'm excited to present HyperPill, our paper about fuzzing architecture, fuzzing arbitrary hypervisors, whether they're open source, closed source, on a particular architecture by leveraging the hardware virtualization interface. So hypervisors allow us to run multiple virtual machines or VMs on the same underlying physical machine. And we trust these hypervisors to provide a layer of security in between these VMs so that if one of our VMs goes rogue, the hypervisor continues running the rest of the VMs in a safe way. And if the hypervisor fails at this task, a rogue VM could potentially compromise the underlying host and the rest of the neighboring VMs. So in order to prevent this nasty scenario, we want to ensure that the interface that the hypervisor exposes to the VMs is safe. And that's the virtualization interface or virtual devices. And in general, this interface is very heavy systems code written in languages such as C or C++. And hypervisors are, of course, used in the cloud, but they're also used for things such as personal computing and vulnerability research, and even making their way into cars these days. So we really want to make sure that we're applying the state-of-the-art automated bug-finding techniques to identify bugs in hypervisors so that they can be fixed way before they make it into a release. And today, the state-of-the-art techniques for finding bugs automatically and the ones that perform best are fuzzers. But if we look at applying fuzzers to hypervisors, we see that there are many challenges. First, we'll come back to this point in a little bit, but the input space that the hypervisor exposes to virtual machines through these virtual devices or this virtualization interface is quite complex. So it's difficult not just to harness a single hypervisor, but even to harness a single virtual device that a hypervisor provides to VMs. Secondly, there are many hypervisors. As we just saw in the previous slide, the type of hypervisor that you'll be using on the cloud will probably differ greatly from the one that you're using on a personal machine, which will have user-friendly features. And that will, of course, differ a lot from what you'd see running in an automobile. And the implementations of these hypervisors are diverse as well. So you can have a hypervisor that runs on a general purpose operating system using a kernel module and a single user space process. Or you could have a hypervisor that relies on a microkernel and actual full VM to perform the emulation inside of it. So developers really have a lot of flexibility with how they want to implement their hypervisor and virtualization solution. And hypervisors are also low-level system software. So that means that we can't really apply a lot of the techniques that general-purpose fuzzers excel at, such as in-process fuzzing or fork servers, because those are tailored more towards small user space libraries or parsers, whereas hypervisors are often made up of many different components, and they're quite large systems, which don't really fit into these types of mechanisms. And finally, hypervisors rely on sophisticated CPU features in their architecture in order to be able to provide near-native performance. And that's really what's allowed hypervisors to gain so much popularity over the past 20+ years. But in this paper, we actually take this last challenge and we look at it from a different angle. And that's the fact that on a particular architecture, every single hypervisor that wants to be able to provide this near-native performance has to use an identical CPU interface. And we'll see why that's important in a bit. First, let's cover the input space. So what interfaces do hypervisors expose to VMs? And really, how do hypervisors allow VMs to communicate with the outside world? Because this is going to be the attack surface. Well, first we have the port I/O and model-specific register input spaces, which basically allow a VM to use a special instruction to trigger an exit into the hypervisor, and then the hypervisor has to emulate this request. Next, we have memory mapped I/O, where the hypervisor can set up parts of the guest memory in such a way that when the guest accesses these regions in memory, this will trigger an exit into the hypervisor, which again needs to be emulated. We also have hypercalls, which are specific to virtual machines, and hypercalls are kind of this rapid method of communication between VMs and the hypervisor. And the way that they work is that there's a special hypercall instruction, and each hypervisor can decide on their own kind of calling convention and which registers to use to communicate arguments in between VMs and the hypervisor. And last but not least, there's also direct memory access. So direct memory access allows the hypervisor to interact with any region in the guest memory while handling any of these other requests. So while handling a MMIO request, for example, the hypervisor can go ahead and read data from the guest memory as well. And this counts as part of the input space. And DMA is really what makes high-performance applications such as storage, networking, display possible. And furthermore, an interaction with the virtual interface is not just a single port I/O operation or a memory mapped I/O operation. Generally, to create a meaningful interaction with this virtualization interface, you have to have multiple operations that are chained together, and they can rely on each other. So for example, a port I/O operation can create an MMIO region, and then an interaction with this MMIO region can result in a DMA access. So we see that this combined input space, accounting for the port I/O space, the memory mapped I/O space, the gigabytes of guest memory, it's enormous. And also it's semantically complex because of these dependencies that we just talked about. But how does virtualization work again? So this is the simplified picture. You have a hypervisor that's running multiple VMs. But let's look at this from the perspective of the architecture of the CPU as well. When the hypervisor wants to run a VM, it actually configures some structures inside its memory. On Intel x86, this is called a VM control structure. And by looking at the structure, the hypervisor encodes things such as the guest's virtual CPU state, the memory that's allocated to the guest, the MMIO regions, and in turn, the CPU actually communicates information about the VM state in this VMCS as well, such as the reason a VM exited. So when the hypervisor wants to enter a VM, it actually uses a special instruction. Here, it's written as VM enter. And the CPU takes over control. It inspects the active VMCS, and then it begins running the guest. And then when the guest triggers one of those VM exits by using one of those modes of I/O, again, that goes through the CPU, which updates the VMCS to reflect the state of what happened, what the VM exit reason was, and then passes control back to the hypervisor. So what we can see from here is that every single hypervisor on a particular architecture has to use the same interface, and this interface encodes a lot of really interesting information about the VMs that a hypervisor is running. So our fuzzer, HyperPill, leverages this fact to fuzz hypervisors generically. HyperPill works in 3 stages. In the first stage, we collect a snapshot of the hypervisor as it's running a VM. In the second stage, we inspect this snapshot in order to perform some enumeration to list some of the input spaces. And in the third stage, we actually perform the fuzzing of the snapshot that we collected and fuzz the hypervisor. So when snapshotting the hypervisor, we have 2 questions we want to answer. When do we want to collect this snapshot? And also, how are we going to collect the snapshot? Well, the best time to collect a snapshot of the hypervisor is just as it's about to start handling input from the VM, and that's when a VM exit occurs. So we want to trigger a VM exit and collect a snapshot precisely at the moment that the hypervisor is about to start handling that VM exit. Well, how do we do this? We add another layer of virtualization. So we have a hypervisor that's running a VM, and we use our own hypervisor, and we nest the target hypervisor inside our hypervisor called HyperPill snap. And our hypervisor is really simple. It forwards all the VM exits as they would normally happen to the target hypervisor, except for one particular type of hypercall. And when we see this special type of hypercall, we pause the hypervisor and the guest that it's running, and we collect a full system snapshot of the target. And when we collect the snapshot, the next instruction that's going to run on the target hypervisor is it about to start handling the VM exit, which in our case is this type of hypercall that we inject. So in the second stage, we inspect the snapshot. Our snapshot contains all of the memory state and the register state of the hypervisor, and it contains the information about the VMCS as well. So by looking at the VMCS and by performing some probing as well, we can identify the memory mapped I/O regions, the port I/O regions, and the memory that the hypervisor allocated for the guest to use. Finally, in the third stage, we fuzz the hypervisor. So as I mentioned, a meaningful input is a sequence of I/O operations, and our snapshot is the snapshot of a hypervisor that's about to handle this strange hypercall that we called. So how can we use the snapshot to actually fuzz arbitrary sequences of hypercall or of I/O operations? Well, we take our input from the fuzzer, which is a sequence of these I/O operations, and before running the snapshot in an emulator, we actually modify the state, the VMCS state inside the snapshot to reflect the type of I/O operation that we want to inject. So in this example, the first operation is a memory mapped I/O operation, so we'd modify the VMCS to reflect that. And then we resume the snapshot running in a full system emulator, and we wait for the hypervisor to handle the I/O request. And if everything goes well, the hypervisor will handle the request and re-enter into our VM. And when that happens, instead of actually running the VM code, we immediately take the next operation, which in this case is port I/O. We modify the VMCS again, and we again trigger VM exit directly into the hypervisor. And we do that until we go through all of the different types of operations in our input. So that allows us to inject port I/O, memory mapped I/O, MSRs, and hypercalls into our hypervisor. There's some more detail that has to go into how we inject hypercalls, but for details about that, please see our paper, because I don't have time to go over that in a 13-minute talk. But we're missing the DMA part of the equation. Remember, the DMA is the type of I/O that isn't associated with a VM exit. A VM exit doesn't, there's no VM exit tied directly to DMA. Instead, DMA is initiated by the hypervisor by just accessing the guest memory while it's handling one of these other types of requests. But in the second stage, we identified all of the memory that the hypervisor allocated to the guest. And since we're running in an emulator, we can check if every single individual instruction that's running is interacting with the guest memory. And if an instruction reads from the guest memory, we can populate that region in the guest memory with fuzzer-provided data, which is contained in the input alongside the I/O operation that actually triggered the DMA access by the hypervisor. And with that, we're able to fuzz all of the major input spaces for hypervisors. We looked at 3 hypervisors. We took the 3 major operating systems on x86 and looked at the canonical hypervisors on them. So Linux is a QEMU KVM. On Windows, we looked at Hyper-V. And on macOS, we looked at Apple Virtualization Framework. And we compared HyperPill to other state-of-the-art approaches on a coverage benchmark over QEMU, which is kind of a standard for comparing coverage. And HyperPill achieves higher coverage than previous approaches, including our own, for 10 out of 12 devices. And this was surprising because, first of all, HyperPill has an inherent performance penalty because it's running in full snapshot emulation mode. And upon digging deeper into this, we saw that this is because the previous approaches rely on source-level hooking in order to be able to fuzz DMA. And by doing this source-level hooking, there's not enough granularity to be able to inspect byte-level DMA accesses, which is what we're able to do with HyperPill because we do this at the instruction level. Overall, HyperPill found 26 bugs across all three hypervisors, and they range from things that could result in denial of service to memory corruptions. With HyperPill, we can reshape hypervisors and fuzz them by using the CPU virtualization interface. And that allows us to fuzz any hypervisor in a particular architecture across all major input surfaces. And it's more precise than source level reshaping. And with that, I'm happy to answer your questions.